Now let us look at some more application of the first law. In the thermodynamic process, they may consist of many processes, but the most process that we always encounter is one or more process in this example. The first one is the process that we call the adiabatic process. The adiabatic process. In the adiabatic process, we define it as a process that Q is equal to 0. And this always happens in the case that the system is in the container which is a thermal insulator. Okay. The thermal insulator. But we can also have the approximately adiabatic process. In the process that happen quickly, or the process that happen very fast. Because in the process that happen very fast, the heat may not be able to escape or enter the system during the process. So we can also say that if the process happens fast enough, it is approximately a adiabatic process and Q is equal to 0. This the practical example in this case is that when you have the bomb and the chemical process is happen very fast and the heat cannot leave or enter the system during the process, and we may have the adiabatic process in that case. Now, once we have that Q is equal to 0, we must have that the change of the internal energy is equal to the work done on the system, because there is no heat, right? So the change of the internal energy depends on the amount of work done on the system. If there is no work in the system, for example, in this process, that is the cylinder here made from the thermal insulator, and we have Q equal to 0, and we have the adiabatic process. And here, when we break the membrane here, the gas expands freely. So in this case, we say that this is a adiabatic free expansion. The adiabatic free expansion. And you can see that in this case we have Q equal to 0, W also equal to 0. So in this process we must have that if the gas in the pistol is the ideal gas, we must have that the change of the internal energy. Sorry, it's not necessarily that the gas is the ideal gas or not, but since we have Q equal to 0, W equal to 0, for any kind of gas, we must have that the change of the internal energy equal to 0. This follows directly from the first law. Okay. The adiabatic process also happens when we look at the process of the phase change. Sorry, not the phase change, but the energy exchange in the engine. As I have mentioned before, that if the process happens very fast, okay, like in the engine, in the stroke of the engine, so heat cannot leave or enter the system, and during the chemical process inside the engine, we can assume the adiabatic process during the process of the engine. We can also have the isobaric process. The isobaric process. In the isobaric process, we have that the pressure is a constant. Many processes that happen in the open air, we can assume that it is an isobaric process, and the pressure is equal to the pressure of the atmosphere. Okay. So, in the isobaric process, since the process P is not zero, sorry, P is a constant. So, if you draw the PV diagram in the isobaric process, you must have a horizontal line like this. And if you look at the process, that the gas change from Vi to Vf, Vi to Vf, okay, we say that the work done on the system is equal to the minus of the integral of P dV, or is equal to the area, the minus of the area under the curve. So we have that W is equal to the minus of P Vf minus Vi. Okay, here you can see that since P is a constant, the integration is the integration of the volume, and we have that the integration is equal to the P Vf minus Vi. Okay, if we go into the little bit detail on this, we have that the integral of P dV, but P is a constant, so it's equal to the P of the integral of dV from Vi to Vf, and this equal to the P of Vf minus Vi. Okay, so we have the W, the work done on the gas, is equal to the minus of P Vf minus Vi. This is for the isobaric process. We can also have the isovolumic process, that is Vf equal to Vi. Okay, if Vf equal to Vi, we must have that W is equal to 0. Okay, and then since W is 0, it means that we have that the internal energy, the change of the internal energy, is equal to Q, because there is no work. So the heat enter or leave the system will change the internal energy of the system. Okay. And for the last one is the isothermal process. Isothermal process is one of the most important process because it is a process that we keep the temperature of the system fixed, or T is a constant. Okay, and if this process happens frequently in the practical system because it is easy to keep the temperature to be a constant. If we make the system with the at the thermal contact with a reservoir, we can keep the temperature of the system fixed. Okay. In this isothermal process, if the gas that we are involved is the ideal gas, we can show that using the kinetic theory of gas in the next chapter. We will have that for the ideal gas, in the isothermal process, the change of the internal energy is equal to 0 if the temperature is a constant. Or we can say also that for the ideal gas, the internal energy of the ideal gas is the function of the temperature only. This is for the ideal gas. So, the change of the internal energy is equal to 0. It means that we must have that Q is equal to the minus of W. Q is equal to the minus of W. Okay, so this is the that is the amount of heat that enter or leave the system must equal to the work done on the system.